So I'm going to go ahead and introduce myself. My name is Drew Cameron. I'm a Python developer, software engineer at Unidata, which is a UCAR community program. I work with Ryan and Nicole here every day, lucky group. I've been at Unidata for about a year, but I was lucky enough to get to study weather and climate before that, and then get to do Python every day. So if y'all want to take a chance to introduce yourselves, then I'll talk a bit more about the notebook when it comes back around to me. And we can get started.
Sure, I'll go next. Hi, my name's Ryan May. I'm also a software engineer and developer for all things Python at Unidata. I've been here 7 years after spending too many years working on undergrad and graduate degrees in meteorology at the University of Oklahoma. I did a lot of radar stuff, and now I do Python all the time. So I was responsible for creating MetPy in grad school and then bringing it back to life when I got to Unidata. And so that's what we're here to talk about is MetPy today. And on to Nicole.
Yes, hello everyone. My name is Nicole Corbin. I am an educational designer here at Unidata. So I get to work with the lovely team of MetPy folks here with Drew and Ryan on delivering and creating these materials here for you today. So much like these other two guys here, I do have a background in meteorology. I studied at North Carolina State University, and then in the last several years really got into learning science and instructional design. So I'm really happy to be here and combining my two favorite things with you all. I hope you really enjoy your time here today. And with that, I will swing it back over to Drew to talk about the notebook.
Before we do that, we did have a question about Unidata. So real quick, I'll give the elevator spiel about Unidata. So Unidata is a NSF or a program funded by the United States National Science Foundation. And we're funded primarily to serve the US universities to help them get access to data and to have tools that make it easier to work with data. So that's doing everything. So we do real-time distribution of data in what we call the IDD, the Internet Data Distribution. And so that's taking real-time data feeds from the National Weather Service and a variety of other sources and sending them in real time using a tool called the LDM to all the universities that run that. We also work on a variety of other tools that help working with all sorts of atmospheric science and Earth system science data those range from like NetCDF, which is a file format for working with data and storing it easier to use than many other formats we work with in the atmospheric sciences. It also encompasses tools for serving data like threads that we'll play with today, as well as a variety of end user tools such as AWIPs that we work on, repackage that from the National Weather Service, as well as another desktop application called the Integrated Data Viewer, and then lastly, all of our Python libraries that we'll be working with today, namely MetPy and Siphon. And so it's just kind of end-to-end. We do all these open source tools that are freely available, and we're happy to support not just US universities using them, but all of our users of those tools. We're just primarily focused around communities involving our primary users from the US universities, but we work extensively with private sector, government, international users as well. And so that's Unidata in a nutshell.
All right. So I'm going to briefly introduce the notebook and how we're going to do things a little differently today from last week. I will mention, of course, we do still have the wonderful Damien, Kevin, Sarah. Looks like maybe Kathy isn't on today, not sure. No, looks like not. But the people that helped you out all last week, you're still stuck with today, don't worry. So today we're primarily going to be working through a Jupyter notebook. We demonstrated a few of them last week and showed you how to start your own, but we didn't work in them a ton last week. So if you ever at any point need to tell us to slow down or explain something, that's fine. Put it in the chat, we'll make it work. You might notice my screen looks a little bit different than a regular Jupyter notebook, if that's what you typed to get here. Don't worry, everything still works the same. And then lastly, so to help us answer specific MetPy and Siphon questions, also to address bigger questions like what is Unidata and who do they serve? Or how do I apply this to X, Y, or Z? Or why won't my data load in to make this plot? We've created a Slido. So I will put the link in the chat. I believe this should work for everybody. This is a place where we're going to have some polls, some quizzes as we go. We've got some interactive activities planned today to sort of break up the code a little bit. If at any point you have a question about getting your code to run, if you have a question about, again, a bigger scale question that we can get to after the exercise, if you just need to know how to reach out to us, etc., try going here. You can post anonymously or you can sign in and identify yourself if you need us to be able to know your name. You can post a question here at any point, and whoever's not teaching at the time will try and keep an eye on it, get questions answered. This is not necessarily for emergency usage. People might not be able to get to it very quickly, so you can still use the chat if needed, but this is a tool available to us, and we will be using it. So at least get it open so that we can quiz you guys later. So if there's no other headaches with getting the notebook open, then I'm going to introduce what we're going to be doing today, and I will walk us through the first brief activity leading to a short breakout room. And yeah, I think we're good to get started. So we've provided a notebook for you that has a lot of text in it, has a lot of code in it, has places for you to put in some code necessary to make it work. We're going to walk through all of this as we go. This is how we're going to spend the whole lesson today. Our goal today is to try and make this plot. If you have any issues seeing this, it should be coming across fine. If not, let me know. But this is this is a weather map we made by hand with data from, at the time it was about a week ago, but we'll be using today's available data where possible, of satellite imagery, cloud moisture imagery, as well as RTMA analysis, real-time mesoscale analysis, and METAR produced station plots for surface observations. I'm going to take a moment to mute everybody else. There we go. If for some reason it muted me, let me know. To get there today, we have, if you look at the top, a few main steps we're going to go through to sort of dissect each part of this along the way. If you're browsing in Jupyter Notebook or in Jupyter Lab, you should be able to click these links. I guess not in Jupyter Lab, I just lied to you. Should be fine in Jupyter Notebook. You should be able to click these links and they take you to the different sections as we go, and you can navigate around if that's helpful. We've got three main steps that we want to get through to make this plot by the end of the day. That is, we want to check out what it takes to plot the satellite data on its own, check out what it takes to plot the RTMA data or the Rtma output on its own, and check out what it takes to read in and plot METAR surface observations. For each one of those exercises, we've structured it in a way that we can, that we think is applicable to most people trying to do atmospheric science, and that would be that you need to get the data, you need to obtain your data, you need to sort of massage it, make it work. You need to prep it somehow, or maybe you do some calculations, and then you want to visualize it. So for each of our exercises, we're going to repeat these. Step A, get the data. Step B, prepare the data. Step C, visualize the data. So you can see our map for the day is laid out at the top of your notebook in big, beautiful, bold graphics that we're going to obtain, prepare, and visualize our satellite, RTMA, and surface obs. And then at the end, we'll have the big putting it all together for one sort of production, publication, communication quality plot. So if there's no questions about what we actually want to cover today, then I will take us through the beginning exercise, and then we will have a brief breakout room activity in just a moment. No screens in the chat. So the first thing that you'll find most people doing before some sort of Python data analysis is figuring out what pieces and packages of the Python environment you need to make your code work. We've put all these at the top. You don't have to, but that's what we've done here today. So we're going to import date time. We actually don't need Python IO anymore, but we need some MetPy IO. Don't worry about it. Cartipy for our fancy georeferenced plots, Matplotlib to actually make them. MetPy for reading in and doing calculations on meteorological data, and Siphon, which is another Unidata product used to get data from a Threads data server. If you've never interacted with one, don't worry about it. That's the very first thing we're going to do is we're going to take a look at how we might go grab data from a Threads data server. So this whole cell, this first cell right here, is what we need to import all of our Python packages to make our code work. So if you've never used Jupyter Notebook or Jupyter Lab before, to actually run this cell, so far it's not been run, there's nothing magic happening in the background. I can either click this play button at the top, or if I'm in the cell and you see it highlighted here, I can hold Shift and press Enter, ignore the loud keyboard, and you will see it pauses for a second, runs the code, now it's done. You just gotta trust me that it's done, but I can also, if you really needed to, I could show you daytime does exist. That's nice. Okay. So we can either scroll down with a mouse or use our arrow keys, however you're most comfortable. We're going to continue going through the sort of text we've provided in the notebook. This is something you can do yourself if you're ever making a Jupyter notebook to share with other people. But we've provided some text here because the next thing we're going to do is we're going to go straight into a breakout room activity. And that's because for each of these exercises, we're going to be using Siphon to get data from somewhere on the internet. If for some reason today you don't have internet access in your Jupyter server, like if you're using it remotely or in a virtual machine, or if for some reason you can't access this data, let us know. We can provide you something to follow along with. But otherwise, we hope you're able to get some real data as we're going and keep up. But as an exercise in figuring out where we need to go to get data, say from our Threads data server, we're going to prepare some breakout rooms. What we're going to do is, if you've got the notebook up in front of you, you'll have these instructions, but I will walk through what we expect really quick. We're going to separate into breakout rooms. You'll still have a facilitator in each room that can help you if there's any issues, but we hope that you as a group will go to this link, threads.ucard.edu. This is the Threads data server we are running at Unidata. There's a lot of different data you can get to from this Threads data server, but we're going to have you navigate to this link in your browser. You'll be presented with what looks sort of like a file browser on your computer. And we're going to have you try and navigate and find the data we're going to be working with today and answer a couple questions that we've put in the notebooks here for you along the way. As we go, you can double click or press enter to interact with this cell in Jupyter, and you can type your answers in to keep track for yourself. But what we'll do is in the breakout rooms, not your facilitator will have one of the participants step forward as sort of the communicator for your group. Basically, as you all as a group come up with the answers to these questions, one of you just write them down, and as we wind down, we'll have you share the answers to these questions with us in the chat to make sure that people were able to navigate the website correctly and whatnot. So I think if everyone's ready, we can separate into breakout rooms. Okay, if you cannot hear me and if you cannot see my screen, let me know in chat. Otherwise, I think we can debrief that activity real quick and then dive back in. We're back up to 48 attendees, so I think, except for a few stragglers, we are good to go. Yes. So I want to, before we start soliciting some answers from the chat, hope you all picked someone to speak up on your group's behalf. We will be judging. That's not true. This was an introduction to what it might look like to browse a Threads data server to get your own meteorological data. This may not be a part of your workflow, but we thought it important to introduce what this might look like, especially because we're going to be using it to get this satellite data and this RTMA output that we had y'all find. So if we want to really quick go through these answers in chat, maybe one at a time, could we have a volunteer that was chosen for each breakout group be ready with their answers, share with the group? So the first and foremost, we need to define the URL from the Threads data server. So we dug through these folders, hopefully. The URL for the current goes east cloud and moisture imagery. We wanted it for CONUS, and we wanted channel 2. So can someone from each breakout room share the URL that they dug up? And we can clarify in case there were any issues finding it. All right, Group E was the first. Group C second. Sorry, Group C, a little slow to the draw. See lots of channel 2s, see lots of CONUS. It looks like Group B, you may not have grabbed the cloud moisture imagery, but that's okay. You were close enough. Oh, just a moment. Okay. All right. Secondly, when you found this URL, when you navigated to these data, you would have figured out, or you would have been exposed to what file format the data were stored in. So can someone from each group give me an idea of what that file format was? Yes, so these data, the satellite data, are stored in netcdf or yes, .nc files. Then we moved on, we went back up to threads.ucar.edu and we needed to find the RTMA output. Can someone from each group share the URL they found for the full collection of RTMA output for the United States? Yes, looking good, looking good. I don't see any Guams in here, so we kept it to CONUS. And then lastly, spoilers, these are in a different file format. Can someone from each group let me know what file format these data were stored in? Thumbs up, good job, breakout rooms. For the remainder of the day, unless we find some extra time, that is the only breakout room activity we have planned. We have many other activities planned, so be on your toes. But hopefully we shouldn't have to do more leaving and rejoining today. Yes, so real quick, since I'm already sharing my screen, I can show you how to get to the RTMA output, Angela. So here at threads.ucar.edu, if you can see my screen, I will zoom in a little bit. RTMA is a sort of model forecaster analysis, falls into this category. So we're going to go to forecast products and analyses. Right here in the middle, you'll see real-time mesoscale analysis. We're not looking for Guam. We're looking for not Guam. This is CONUS. This is the rest of the United States. Here you'll see a collection of RTMA output for CONUS for today. Or I guess this is for February. If we scroll down, we can get to today. At the very top, without the little file folder icon, is a full collection data set, which in the notebook is what we requested you to find for us, the RTMA full collection. So if you click this link, you'll be presented with a whole bunch of catalog information that we're not worried about you deciphering. to get here. But so that is generally what it might look like to navigate a Threads data server. We're now going to interface with that without looking at those pages again. You can if you want to, but without having to, using Siphon and Python. We're not too worried about the details here, but for every one of our products that we make today, we're going to use Siphon to get data from this Threads dataset. So I'm going to hand it off to Ryan, and he's going to introduce how to obtain and take a look at the satellite data that we navigated to. And yes, steal my presentation. And yeah, we'll go from there. The first step to making our final fancy publication plot.
All right, am I actually sharing my screen properly here? Okay, good. Okay, so
It's your full desktop if that matters. And if you could,
that's good to know.
yeah, if you want to share just the browser window, and if you could zoom in for us.
Yep. Well, I did select just a browser window, but that apparently didn't work. So, okay, so satellite data. So that's the first layer of data we're going to be trying to get access to and plot. And so the theme of the day is get data, prepare data, visualize your data. And that's kind of the standard way most, at least my data scripts ends up looking. Do a whole bunch of work to get a hold of data, do whatever interesting things I'm trying to do to get ready to make a plot, and then 9 times out of 10, especially when we're working in atmospheric science, the goal is to have a plot come out the other end. So first part, obtain satellite data. So this first cell here, we have just a couple lines. And so this first line is we're setting up what we call a Tds Catalog. So this Tds Catalog is a class that comes out of Siphon, and its mission in life is to handle accessing one of those Threads catalogs we just played with, parse it, and provide relatively easy programmatic access to the data that's in there. And so we'll see here in this long URL, this is the URL you came up with in the breakout room, with the one difference being instead of ending in .html, it ends in .xml, because the code wants an XML document to work with, and Threads data server can provide those. So we have that long URL we found by clicking around the catalog and found the data we were looking for. We take that URL, hand it to Tds Catalog, and it goes out and downloads it and parses it for us. Second line of code here, this is when we're going to get the data we actually want out of that catalog. So we take, we save the Tds Catalog as satcat. And so we say satcat, the catalog has this .datasets attribute. And so we say .datasets, and that has, that's a, you can think of it as a list or a dictionary, a collection of all the data sets that are available in that catalog. And we do square bracket 0 to access the first or most recent data set that's in that catalog. So we get the most recent image. And then we're going to chain on the back of that .remote access. That tells Siphon to go ahead and give us back something we can use to remotely access that data file. And we pass use xarray equals true here to tell it we want to use xarray to access that data. And so this will give us back an xarray data set pointing at that remote data. So I'm going to run that cell. And note, it didn't actually go out and download all the data when I did that. Instead, what it did is it used a service, a couple different services, or one of a couple different services, either OpenDAP or CDM Remote, that provide remote access to data. And that initial step, it doesn't need to go out and download all of the full image. It just downloads some metadata about it, maybe a bit of the information about the dimensions that are in the data set and whatnot, but it doesn't need to download the full thing until we actually use the data. So it's going to be a very efficient process to just point to the data set and one of the nice things is there was no need to go manually download a file and figure out where on disk that file was and figure out the path from our notebook to that downloaded data file. Instead, we could just point to the data file and start working. All right, so we accessed our data. Now we want to prepare it. So in this particular aspect, we're going to just do a couple simple steps here. The first step we're going to do is we're going to pull out the array of data we're interested in. Here, if we look at our sat data, we see we have this data set, we have some coordinates, some data variables. Really, there's only one data variable that has more than one dimension with this y, x here, and that's sectorized CMI. So that's our imagery data that we want. And so we're going to pull that out. Instead of, as we worked with X-array last week, instead of directly accessing, sat data dot sectorized CMI, we're going to use some helpers from MetPy here. And so because we're working with X-array and we've imported MetPy interfaces with X-array and sets up some helpers on X-array here, all coming under this .MetPy attribute that's hanging off our data set. We say .metpy.parsecf, and then we give it the name of the variable we want. And what that does is that looks at a bunch of the netcdf metadata and tries to interpret the metadata and do some nice things so that it can automatically understand things like, in this case, the big one is the projection information, so that it knows what the projection of the image data are, because we're taking imagery of a spherical Earth, and you can't uniquely map from a three-dimensional sphere to a 2D plane. There are different geographic projections out there. And so this handles looking at the metadata, figuring out what the proper projection is, and making that available to us later. So here we pull out the data we want, interpret the metadata. And then one other thing we're doing here is we're going to get the date and time out of the file. So if we look, I'm trying to see it. It lighted it here, but if I print set data, so the satellite data set has this attribute that's the start date time of the image. 2021, okay, that's the year. 068, well, that's interesting. 194615, that looks like a time. That's reasonable for the most recent image. So that's the time. That's the year. So 068, if you're not a satellite person, you're not used to this, but this is what we call the Julian day of the year. And basically it's a counter that starts at 1 for the first day of the year and goes forward. And so that's what 68 means. We are the 68th day of the year. I don't want to go into too much gory detail here, but we can use datetime modules string ptime or string parsetime method, and we can hand that funky datetime string, and we can tell it how to parse it with this, which is the quick explanation is that tells it look for the year, four-digit year, Julian day, hour, minute, second, and it parses that and gives us that as a Python datetime object we can work with. All right, last but not least, now we've got our data, we've done some steps to make it easier to work with, so now it's time to plot. And so I believe we hit some things using plotting images last week, and so we're going to use Matplotlib to display our data here. So what do we need to make a plot? We need to know what is the name of the data array variable we need to plot, what Matplotlib function should we use to make the plot, and how do we correctly, what's the right syntax to use to call that function. So the goal here is we're going to spend about 5 minutes here plotting up the satellite data. So I'll give you some time to look at the data we've downloaded and see if you can figure out how to call the Matplotlib function to plot image data, and type that in the cell below and see if you can get image plot, and then we'll talk about it in just a few minutes.
Oh, I was just going to say there's some questions coming up in the Slido real quick. If we want to address them vocally, it's fine. If not, but basically someone asked if we can use Siphon to access other threads data servers besides Unidata's. Yes. So like NCEI's threads data server, you can access with Siphon. We have a lot of examples for these. We can share them with you if you like. And then another question was how might we use MetPy on local data, on data you have downloaded or generated on your own computer. It depends. You can do it for any of these. And the easiest way might often be if you're working in NetCDF to read them in as an X-array data set or data array, and then follow the steps similarly to what you see here. Basically, we're using Siphon to just get an X-array object from the threads data server. So anything you see from there should work on your own local data, of course, depending on how it's set up. But basically, there's no reason you can't. We might just need to figure out what it is you need to make it work.
Okay, and with that, I should probably start typing out some answers here. So what's the variable we need to type in here? What are we trying to plot? What's the name of the variable we're trying to plot here? If you want to type it into the chat. Okay, so it is CMI. So then for CMI, then what are we using to plot it? What's the Matplotlib plotting function we use to plot an image? Okay, I see mshell, contour F, can use contour F. Satellite data, the contours could be a little noisy, but not a bad one. Scatter is interesting because you don't usually use that for regularly spaced points, but there's nothing saying you couldn't. It definitely depends on what you're trying to accomplish. Plot's good for 2D line plots. So the one we're looking for here is mshow, because that's going to actually plot the image with just a continual grid of pixels together. And we'll see what that looks like in just a second. And so we need to make sure we put the PLT dot in front of it so that we get imshow out of the PLT namespace here. So if I run that, now my computer is going out and downloading all that image data off the server, and then parsing it, and then it's going to make a plot eventually. And while that's doing its thing, which I'm not sure why it's taking so long, but I'll let it go. There we go. So there's our plot, and that's using the default color map from Matplotlib called Viridis. And that's a perceptually uniform, color deficient, vision safe color map. And so, you know, it's not bad, but blues and greens aren't necessarily what we want for this satellite image. So frequently we want grayscale. And so bring a chat back up here. We can do PLT imshow CMI, and then anybody want to volunteer what they added if they got here to change it to grayscale? There we go. There's a taker. We can do gray. That needs to be a string, so I need to put it in quotes. No, that's not what I wanted. That's what I wanted. Okay, run that. And what did I do wrong? I spelled gray wrong. That's what I did wrong. So if we scroll down the error message, we get value error. Gray is not a valid value for this. Then it gives you a full list of all the Matplotlib color names. So that's because I mistyped, and I should be GRAY. And now we get something that looks more like what I'm expecting. So that's that. Drew took care of the questions that were sitting there. So I think that's it for satellite data. I think we're ready to move on to the model output.
All right, I'll steal the presenter back away
If you
from
can.
you. Okay. Can everybody see me, see my screen, read what we've got? I followed along. So I'm down below, step 2. All right, perfect. Jonathan, that's a good question. We'll talk a bit more about coordinate transforms later, because we do have data in different projections here, and we need to get them to all cooperate when we make our final plot at the end, but we'll get to that later. Cecile, not necessarily. There are some, say, Matplotlib color maps. I think we have an example somewhere that uses gray, Grey. It kind of depends on the creator of the color map and the package used to get whatever it is you're looking for. Basically, no, not necessarily. Okay, so we have gone through our first major exercise in that we've obtained, we've sort of massaged, and we visualized our satellite data. Now we need to repeat those steps for our Rtma output. Similar to before, we're going to again obtain the output using the URL you found in the previous exercise in the breakout room exercise. Then we're going to this time prepare it by doing some calculations. And then we're going to again play around with visualizing it. There are multiple activities in this section because we're going to demonstrate multiple features and pieces of functionality that MetPy has. So we'll get started. So we are going to reference the URL that you all found for us earlier. Thanks for that. To once again create our Siphon Tds Catalog object. Similar to satellite, we're going to navigate and find the different data sets in that catalog. This time, instead of just pulling out the 0th data set, we're specifying one by its name. So at the top of, if I go back to forecast products analyses, Rtma, we have this full collection data set. We're going to reference that full collection data set. And then similarly, we're going to access it remotely, again, using Xarray. Just like before, to enable some of our nifty, particularly to use some of our nifty geospatial parsing that we've provided in MetPy for y'all, we're going to use the xarray.metpy.parsef function to get our data and put it into an Xarray data set. So let's get ready to dive into the first activity. And we've gone and pulled down this data set of Rtma output, but we don't really know what we're working with, what we have access to, what it looks like, how we need to navigate it. So we have a brief activity for doing this. So if you've worked with Xarray earlier today and last week, the first activity is just let me set aside a few minutes for people to figure out how they might use this space here to examine the data set you just grabbed from Siphon. What might you type into this cell to get a preview of your data? And then after just a minute or two, I will get some responses in chat to help me figure out what it looks like. All right, so we'll go ahead if people have had a moment to play around with it. Yes, we've got a few people running ahead. Let's take a look at our data set. If you're working here in a Jupyter notebook, per David's suggestion, we can just type in the name of our Xarray data set and get this nifty HTML visualization of the data set. This gives us the, excuse me, the various coordinates, the different data arrays in our data set are indexed by, so they might be on different time coordinates. They might be on different pressure or altitude coordinates. This is our list of the coordinates, or I guess we don't have to worry about pressure in this one. This is our list of coordinates available. In this data set, we have a list of the actual variables available to us. And we have lots of attributes stored in the data set itself. So we can also just use your classic print to get a sort of longer, if I wasn't so zoomed in, this would be formatted a little easier, but just a sort of longer classic text output. So we'll leave it for now. Okay, so next step is we need to pull out the actual data array, the actual individual variable that we want from our Rtma data set, our collection of data, for us to perform some calculations on and get ready to analyze. I'll allow someone else to respond to questions we've got in the chat. But the way we've done this here, and there's a few different ways you can do this, but we'll just walk through what this looks like. We're making a variable called pres, which in this case is short for pressure. So this is our Rtma data, the X-ray data set we just got from Siphon. We want to select the pressure analysis surface variable within that data set. You can do this with, if you're comfortable with Python dictionaries, the bracket quotes will allow you to select this data array. You can also press tab to complete it for you if you want, or you can also just type dot and your variable name. And that's what we've done here. So we have our data set dot pressure analysis surface. Now, like Ryan referenced in the previous section, we need to use some of the fancy MetPy X-array tools we provided to you that will allow us to select data from our data array using common names of the coordinates in those data. So if we go back up and look, you see you've got time, you've got time 1, you've got ref time 2. You, especially if you're pulling down certain model outputs from here in the States, you might get a lot of these differently named coordinates for different variables in your data set. So if we use MetPy's selection, this will figure out which of these your data are indexed along. So basically, maybe our pressure analysis surface, if we go look, pressure analysis surface, it's on time 1. I don't know that. I don't know if it's on time 1. I don't know if it's on time 2. I just want to index based on its time coordinate, whatever that is. So if I use .metpy.select.sel, I can specify time, and it'll figure out which time coordinate I'm working with. Then I can give it the date time object we created in the previous section. So this is saying I want the surface pressure analysis from the time that is, here I've specified method nearest to the same time as our satellite data. We've tacked on here at the end a final dot squeeze. You may have seen this if you worked with NumPy, just to get rid of any extra dimensions that come along for the ride. Say, if we've selected only one time, we don't need that, 200 by 100 by 1 array. We just want to squash it down to 200 by 100. So this will give us our pressure data array. We can, similarly to Rtma data, we can take a look at it. We see it has coordinates X and Y. It's along time 1 equal to 2021, 0309, 1900. And yeah, this is our surface pressure analysis. This is what we're going to be working with for the remainder of this exercise. So now, how might you pull temperature or dew point from this same RTMA data set? We're going to, I think, go ahead and take our break now. Play around with this during the break if you have time. If not, we'll just get back to this once the break is over. But the current activity is to navigate the RTMA data set, find temperature, find dew point, and pull those out for the same time that we did for our surface pressure analysis. So we'll take a pause there. We'll take a 15-minute break, I think, if everyone's ready for that. All right, break time is up. We'll give people just a second to return. And while people are in the process of returning, maybe I could get a few vocal volunteers. So hopefully my screen is still, yes, still being shared. If I could get a few vocal volunteers to maybe offer what creating our data arrays for temperature and dew point from RTMA data might look like. Well, start. All right, I'm gonna go ahead and type what I've got in chat, and then we'll check and see if it works. So this is from David. We've got RTMA data. We're going to use, this is the same thing as our sort of dot notation above, but we'll use the sort of Python dictionary notation here. We'll specify temperature. I've started to type this. Let's see if, yep, I can just mash tab and see what it gets me. We got temperature analysis, height above ground. Similarly, we want to select using metpy.cell the nearest time to our satellite image. Nearest. Then we want to squeeze off any unnecessary dimensions. Similarly, let's take a look at dew point. I'm going to copy David's answer here. All right. The annoying keyboard sounds are how you know we're getting work done. So let's run the cell. No errors, nothing's yelled at me. Let's take a look. Hey, perfect. We've got an X-ray data array with our temperature analysis height above ground and our dew point temperature analysis height above ground. We can continue from here. If there weren't any issues getting these, we need these moving forward. Because the next thing we're going to attempt to do is we're going to use one of MetPy's calculations to calculate the theta E, the potential temperature, equivalent potential temperature from our RTMA data available to us. I'm not going to tell you how to do it, but we do have some pretty good documentation that should explain to you exactly what you need to type in to get this to work. So we're going to take just a moment to let people navigate this site, get comfortable with it, and see if they can find the calculation on this page to calculate theta E, equivalent potential temperature. If there's any questions or issues navigating the website, or if you can't get to it, let us know. While you're here, while I sort of let people roam the documentation, if you've already done this, or you already, or you figure it out pretty quickly, maybe see if you can take a look on this calc page, see what else, given the variables we've selected so far, the pressure, the temperature, the dew point, you could calculate from the RTMA output. That's just sort of a bonus challenge if you want to take a look and mess around. Maybe you can figure out how you want to plot that or make it work for you later. But for now, focus on seeing if you can calculate theta E using our RTMA output. So we'll take just a second to do that. I just received a question in the chat about if we have a mailing list for MetPy questions. Yes, one of our primary roles is to support people using MetPy. We have multiple support avenues for doing so. We can share those with you all in the chat either now or later, not a problem. But we respond to questions on GitHub, on Stack Overflow, tagged with MetPy or Python Siphon. And we do also have a Unidata Python support email that you can reach out to that we will respond to. And so we're going to take a few extra minutes maybe on this exercise, just make sure people have a chance to navigate the documentation website. If you have any troubles navigating it or notice anything interesting while you're there, don't hesitate to share it with us. And we will still be checking the Slido for any questions. So far, is anyone having any issues navigating our documentation website or getting access to it? So Geeta, if you've been following along, you definitely need to have MetPy imported at the top. If you've restarted your notebook and have been following along, you may need to go back up and run that cell again. Or if you had any issues installing MetPy or using the correct environment, we might need to get that taken care of. I might suggest just to keep an eye on things. If you finish this and you've found this on the documentation and you've already typed it in and maybe gotten it to work, if you can, use the hand raise feature in GoToTraining to basically let us get a picture for how many people are just waiting on us. Basically, just raise your hand if you are done. Yes, I was just about to highlight that. For anyone running into the same issue in the chat, it is important to note that we are using metpy.calc. However, at the start, we decided to import that named mpcalc. So if you're using a function from metpy.calc, you'll need to start it with mpcalc, just like you have been for pyplot named plt. And again, don't forget, if you're wrapping this up or have figured it out, go ahead and raise your hand. And if you are having any issues, be sure to post in the chat or post to the Slido. for a few tips for people figuring out how to navigate our docs, our documentation. Note that here I've got the calc page up. You have a nifty full alphabetical list. Actually, it's not alphabetical, it's by category. Of all the functions available to you on the left, or you can just scroll down this very long page. And also we have these categories on the right for you. So if you're trying to find calculations for dry thermodynamics or moist thermodynamics, you can navigate those categories. You also can search the documentation up at the top. If you have an idea that for what you're trying to accomplish, you can probably find it pretty quickly with a search at the top. Once again, reminder for people coming and going, if you have wrapped this up, if you have a function here for calculating potential temperature, go ahead and raise your hand to let us know you're done. If you're having any issues, please let us know in the chat or on Slido. Otherwise, we will resume the activity in the next 2 or 3 minutes. Seeing some people maybe figuring it out in the chat, but I won't tell. All right, yeah, I think this is probably a good time for us to start to continue. Maybe I'll take a moment myself to navigate the docs in case anyone had any issues. Of course, if you did or have any questions, be sure to let us know. But I'm going to start moving forward. So what we suggested is checking out the MetPy.calc documentation. I've already got it open, but if I click that link, we'll go straight to this big long page of functions that you can use to do calculations on your data. Let's maybe, for me, I'm just going to search. I want to do potential temperature. Oh, nice, first one. Equivalent potential temperature, or theta E. Some of our functions will have documentation, formulas, citations, etc., that let you know where these come from. A little plug that we always accept refinement or suggestions or contributions on our GitHub. If you ever see something that doesn't seem quite right or you think needs updating, don't hesitate to let us know. But so I have equivalent potential temperature. This is metpy.calc equivalent potential temperature. So the function is equivalent potential temperature. The things I need to calculate this are pressure, temperature, and dew point. Luckily, we have all these things. So let's go back, noting per someone's point earlier in the chat, to get to metpy.calc, we've imported that simply as mpcalc. Then if I go back and double check, the name of the function is metpy.calc equivalent potential temperature. I'm going to cheat. I'm going to copy it and paste it into my code, so I don't have to type it myself. And then let's go back and check again. I need pressure, temperature, and dew point. A little tip, if you're in Jupyter, you also could go question mark mpcalc.equivalent. I'll press tab to get it done. Run this cell. This will give me the doc string for that function right in Jupyter. So if you know what you're looking for but can't seem to remember what you need to give it, this will tell me I need pressure, temperature, and dew point. So let's do that. Equivalent potential temperature pres. That was our data array for pressure, temp, and a dupe, pressure, temperature, and dew point. Let's run that. Take just a second. All right, it's done. Let's take a look at it. Perfect. We had a question in chat along the way that, oh yes, looks like you saw. Basically, on their own, X-array data arrays do not contain Python usable unit information in them. It might have an attribute with the units attached to it. But if you've used MetPy in the past, or if you've plugged things into a calculator before, you know you need compatible units to make sure that your calculations will come out as expected. And we also require that on MetPy. Now, as of sort of MetPy 1.0, if you've kept up with things, if you have X-array data sets and data arrays with unit attributes in them, we will do that interpretation for you. So we had a question, no, we don't need to specify units for pressure, temperature, and dew point. In this case, it's not universal, but in this case, we don't need to, because equivalent potential temperature will pull that information out of each of those for you, and we get back a data array with theta E in units of Kelvin, you'll see here. So let's work with that. We are going to use, coming out of that calculation, any sort of contours or visualization of our theta E from the Rtma output might be kind of noisy, bumpy, tough to look at, spaghetti on a screen, etc. So we're going to use another mpcalc function, smooth Gaussian, that's going to smooth those data out for us. Again, I'd suggest go checking out the docs if you want to understand what's happening here. So pretty straightforward. We've smoothed it out a little bit. All right. Now, in the previous exercise, we didn't explore any CartoPy features. We just viewed the image of our satellite data without changing its projection or adding any CartoPy specific visualization aids, any coastlines, things like that. We at MetPy have created a little bit of a shortcut to pull out necessary CartoPy information from X-array data sets and data arrays. Ryan introduced this with the .metpy.parsecf in the previous exercise. If you've done this, we can pull out the projection type and any defining quantities of the projection that your data are in from your X-array data set. So that's what we're doing here. We're using theta e.metpy.cartopycrs. So .metpy.cartopycrs is going to create for us, I'll make a new cell here to take a look at it, Rtma CRS, the projection information that CartoPy needs to know about our data. In this case, it is our Rtma data are in a Lambert conformal projection. And so we can use this to maybe visualize our data in a new projection, or to, we had a question earlier about transforming points between latitude, longitude, data coordinates, etc. We'll talk about that a little bit more later. So the next exercise is that given our new theta E, we calculated theta E, we smoothed it out a little bit to make it look a little better on a map, and we pulled out the geographic information we need. So with all of these things, let's take a few minutes for a brief exercise to visualize this using Matplotlib filled contours in this case. You can explore however you want, but to see if people are on the right page, we're going to try and make filled contours of theta E. And then let's see if we can transform it and view it in the Robinson projection instead of the Lambert conformal projection. We've provided the code to do that up front here. So first we have created a Matplotlib Axes object with the Cartopy Robinson projection. So this means we're basically making a map in the Robinson projection. And I can actually just show you what this looks like on its own. Using Cartopy to transform the map itself into the Robinson projection. Remember up at the top, we imported cartopy.crs, similar as to last week as ccrs. From that, we're going to pull out the Robinson projection. Let's take a look at it. Nothing fancy yet, sure. But now I'm going to take these axes, and on them I'm going to plot filled contours, contour F, of theta E. I need to, for contour F, provide the location information for my data. So here, if I go back and look at theta E again, I have X and I have Y, indicating where these data are located in that Lambert conformal projection we just looked at a second ago. So if I give contour F, sorry about that, if I give contour F the X values for theta E, the Y values for theta E, the actual potential temperature values, theta E themselves, and then I supply this Cartopy transform information that basically says, what I'm giving you is in a Lambert conformal projection. I need you to make it work on my map, which is in the Robinson projection. And so Cartopy will perform its magic to show that to you. So let's take a look real quick. All right, it looks different than before, I'll say that. But now the activity to y'all that we've provided this for you. I'm not sure if it was covered before, but how might you visualize coastlines or other geographic boundaries on this map using some features of Cartopy? If you need pointed in the direction of their documentation, or if you might read ahead a little bit in the notebook, you might find this. But let's take a minute and see if we can understand a bit better what this actually looks like. And we'll take just a minute or so here for people to explore getting these coastlines visualized, and then see if maybe I can get a person to let me know what I should try in the chat. Yeah, so we've got a few suggestions in the chat. Excuse me. I see we have an add feature. That is something that allows you sort of more control over what you're adding to your map. But yeah, if you're just playing around or trying to get a quick look at your data, you can just type axes, or the name of your axes objects. In this case, mine is ax dot coastlines function. Let's see if that worked. Hey, there we go. That looks like the United States and a different projection. I call that a success. If you had any issues getting this visualized, be sure to let us know. But starting from here, we're going to hand off to a longer activity to have you all create a contour plot. So instead of filled contours, we'll have you plot just contour lines of theta E. So this is all laid out in the notebook if you need to refer back to this. And we're going to have you plot it in the, let me make sure. Yes, okay. So what we're going to do is for our final plot, we're going to use this Lambert conformal projection that the RTMA data are in. That'll look pretty good. That's what the first thing we showed you was in. So we're going to have you all plot this same theta E data with regular contour lines. And then let's have you plot them in the original CRS of the RTMA data set. So the original Lambert conformal projection. And that is what we're going to use for our final product, is we're going to have contours of our theta E on our satellite data along with our surface observations. So this is sort of an intro to what's coming at the end. Take a second to try this on your own. And yeah, I think that's about it. We'll take a few minutes to work on this. We included a little bit of a challenge here, if you'd like, similar to our satellite exercise. We suggest maybe taking a look at the Matplotlib documentation for colors to see if you can change up the presentation of your contour plot. Maybe make all of the contours the same color. You can also play around with labels, etc., if you like. But we'll take a few minutes to work on this. If you have any issues getting it to show up, let us know, and then I will carry forward in 5 or 10 minutes. So I got a question in the chat about why or how did we create this plot without creating a Matplotlib figure, which is something that comes later in the notebook. You don't need a figure to create graphics with Matplotlib. A figure you could imagine as a container for one or more axes, which are, if we look here, this is an actual axes object. And that might give you control over how the figure is shaped, spaced, the size of it, any things you add to the figure, like captions, headings, titles, etc. It can give you more control, but you don't explicitly have to make one before creating your plot. After we succeed at getting the RTMA data visualized with solid line contours, which is our sort of final goal for the end product, we'll also leave some time for some polls on Slido. So make sure you have Slido open. We'll share that link in chat again. We have some questions for you all before we move on to surface observations. As before, I'll suggest that, here, let me I'll suggest that if you've wrapped this up and you've successfully plotted your RTMA theta E in its original Lambert conformal projection with solid line contours, to go ahead and raise your hand in GoToTraining so that we know that you're done. Yes, we will get that link to you in just a second. And of course, the Slido is open to any questions or issues you're having, or if you have larger questions about how to apply this to more complicated problems, etc., don't hesitate to put your questions or feedback there. And while we have a minute, I'll pull up these Slido questions myself. The only current question in the Slido is about converting data grid points to latitude, longitude. We'll get to that in just a minute. All right, in just the next minute or two, I will start to move forward with taking a look at this myself, see if maybe I run into any issues that other people were. Hopefully not. Get a plot with some contours up, and we'll move forward to a few questions for y'all to sort of make sure that we're getting the right information across before we move on to the last major step, which is getting, preparing and visualizing surface data. So we'll take just a minute longer. All right, if there were no major issues, I will again unleash the annoying keyboard and see if I can get this pulled up on my own. So similar to above, let's start by just making some Matplotlib Axes for us to work on. So we'll just use plot.axes, keep it simple. Here again, we need to specify the projection of the map itself we want to work in. So projection equals. Now, before we typed it all out from creating a default Cartopy Robinson CRS. We could do ccrs.lambert conformal, whatever. However, if we want to just refer to, again, if I scroll back up, the Cartopy object we created with all of the necessary information from our original data, we can just refer to that, Rtma CRS. So projection in this case is just Rtma CRS. Really quick, we can take a look at that. Looks like a Lambert conformal. Doesn't look like much just yet, but let's add something to it. Before we used Matplotlib's filled contours, contour F. This time let's just use contour for just our line contours. In the notebook here, we gave you all a little bit of information to hold on to for if you use MetPy with your data in the future. And that is similar to the .metpy.cell shortcuts we touched on earlier about, I don't know what my time is called, but I know that I want to select by time. Maybe it's time 1, maybe it's time 2, whatever. We can use similarly .metpy.x and .metpy, whoopsie, and .metpy.y to just pull out the x or y dimension of our data, regardless of what its original name actually is. So this might be helpful if you're not totally sure what name the x, y, or latitude, longitude coordinates came through as. So let's try that. We again have to specify our x and our y. So let's do theta e dot metpy dot x. Again, that's a shortcut to just pull out the x dimension of our data, regardless of what its name is. Then let's specify theta e dot metpy dot y to again specify the y dimension of our data. The data itself, theta e, and we still, even though we're working in our same projection as the data, are going to specify the projection of our original data. It might not have to move anything around, but this is for Cartopy's information. We can also go ahead and skip ahead to the challenge here, and we could make all of our contours a eye searing for it blue directly in our contour function here. As before, let's also take this opportunity to add some, if I can spell correctly, coastlines. And there we go. We have contours of our calculated theta E from our Rtma output plotted in solid blue contours on a map of the US. So we're going to take a bit of a pause here to open up some polls on the Slido. These are brief little multiple choice quizzes that can help us make sure we're getting the right information across to you. So again, I'm going to share the Slido link in the chat, make sure you're there. Take a moment to read the question and select the best answer appropriate before we move on to surface observations. And of course, if there were any questions or issues with getting the contours, yes, sorry, contours plotted, let us know. And if people need a quick run through of what it is, what the solution to this was, I created my axes onto which we're going to plot. I specified the Cartipy CRS information that I pulled out before using its name. So I want to plot my data in the same projection that it's been, that it is in. And then I use Matplotlib's contour function for drawing contour lines instead of filled contours, which was contour F. I specified my X dimension, my Y dimension to tell it where each of these data points are. I specified the data themselves. I gave it the Cartipy projection transformation information it needed from the same RTMA CRS. And I told it I wanted it in a bright blue. And then we added some coastlines to it. Yes, so to touch on Gita's question here in the notebook, if I look at the documentation for Cartipy's Lambert conformal CRS, I see that there are a lot of pieces of information we need to provide to Cartipy for it to define this coordinate reference system. There are some defaults assumed. However, if we go back up to, actually, let's go back all the way to, oh, we've already parsed it here. Basically, in our original data, we had this information specified, the central longitude, et cetera, specified in the NetCDF metadata, and we at MetPy took that information and made the exact CRS you needed that your data are defined in. So we populated these parameters to create the same Lambert conformal projection that your data are in. And yes, one last reminder, we have a poll going on the Slido. Please take a moment to respond to it. And I will pass off presentation to Ryan for the surface observations. Oh, importantly, sorry, there are 2 polls live currently, so be sure to respond to both.
Correction, there's one poll live right now, and then we will have the second poll live when we have enough responses on the first poll.
Excuse me. Thanks, Nicole.
Right, the first poll should be ending here. All right, I think I have to activate it here again, but let's discuss the results of the first poll.
Sure. The question was, before preparing meteorological data for plotting, we must first populate the data from the Threads data server into. So the answer we were looking for was the Tds Catalog class. So that was the class we used that we pointed at the XML Threads catalog. And that class downloaded all of the information about the data sets that were available and everything else there. And that was the first step. Then the second step was to then get the data set and ask Siphon to give us that back as an X-array data set. So you have the two separate pieces of the Tds Catalog class talks to the Thread server and gets information about all its data sets. And then the second step is where we get X-array and get it populated using the one data set we've selected out of that catalog. Drew, is there anything else that we should talk about there?
I don't think so. Is there, if there's any confusion there, be sure to let us know.
Yes, please.
Great. I'm going to stop that poll now and then launch our second one here. All right, it looks like we are actually pretty close to unanimous on this one. So let me show the correct answer here, and then we can just really quickly talk about that one.
The question was, you're tasked with creating a plot of frontogenesis over the continental United States using an RTMA dataset from the Threads data server. Which of the below options is the best first step towards this task? And overwhelming choice was look up the required parameters for deriving frontogenesis with MetPy. That was the answer we were looking for. Whenever you're trying to get a task done, the first thing is usually best to go figure out how the tools that you're planning on using work and figure out what they need in order to generate the answer you're looking for. So that was the answer we were looking for. All right, any questions about that before we move on to surface data? Okay, so far we have looked at going to a thread server, getting some satellite data, getting some real-time mesoanalysis data. And so the last step to getting that map we had that had all the different sources of information on it is we want to get some surface observations. And so we'll be doing that. We'll be trying to make a station plot on our map. And there's a link there to what station plots are, and we'll go through what they look like. But these will be a bit different than what we've done so far because, I lost my, there we go. Instead of just pure Matplotlib plotting commands, we'll be doing a bit more using MetPy's plotting. And the other difference with surface observations is instead of being a regular two-dimensional grid, we have kind of an allotment of random points. And so the workflow, however, is the same. we're still going to obtain our data. We're going to do some data manipulation, and then we're going to plot the data. It's just these are going to look pretty different from what we worked with satellite and equivalent potential temperature. So first step, obtain surface observations. So once again, we're going to use our friend, the Tds Catalog class, and we're going to hand it a URL. And this time, we're handing it a URL to some data on our threads testing server. This is where we can get, we call METAR observations. And we'll cover a little more what METARs look like in a second. But essentially, that's how most surface observations are reported operationally these days. It's in this text format, sets of reports, and on this testing server, we've been accumulating these reports into hourly files that we can access and download. So step one, point threads, or point TDS catalog at this thread server catalog so it can figure out what data sets are available. And then step two, it starts out the same. We have this, we store our TDS catalog in metarcat. And then we say metarcat.datasets. And we say, instead of doing square bracket 0 or square bracket full collection, here we're going to use a helper from Siphon called filter time nearest. And what that does is it kind of assumes a certain file naming convention that has a date and time in the file names. And so it can look at all the file names that are available on the server and find the one that best matches the time we're looking for. And so that's what we're going to do here. We're going to use this DT. That's the time we parsed out of our satellite data. And so what we're looking for here is the METAR file that closest matches our satellite imagery time. And then previously we used remote access to open it as an X-array data set. This time we're going to ask it to do remote open so that it can open the file as if it was a local data file, but it's actually not a local data file. But we'll need that so we can pass it to MetPy's functionality in a second. And then we say mode equals T to tell it to open it as a text file rather than a binary file. So if we run that cell, it goes up to the catalog, finds it, and then does what we need to do. So that's the first step. We've gone and accessed our data and gotten what we're looking for. So now METAR text is this, it looks like a text file that we've opened locally. It's this file-like object, as we call it, which just means you can read bytes out of it and do various things to parse the data that are in there. So now, instead of X-array, we're going to work with Pandas data frame because that maps pretty well to how these scattered point data, these what we call columnar data. And we can use functionality out of MetPy, a function called parse METAR file. As you might assume from the name of the function, that's going to help us parse a file of METAR observations. And so we imported parse METAR file at the top from metpy.io. And so we call this function, we pass it our METAR text file-like object. For completeness, we tell it what year these data are from and what month, because METAR reports actually don't contain the month and the year, they just contain the day and the time for reasons. And then we get that back out and store that in SFC data for surface data. And we do a few other data manipulation steps. This surface data frame, if that's a Pandas data frame, MetPy adds a .units attribute on that contains the units for all of the columns that are in that data frame. We're going to save that off so we have access to that later after we've done some other manipulation steps. We're also going to go through a few steps where we're going to take our surface data, and here we're trying to get rid of the stations that are missing. So what we're doing is saying, okay, all rows where the latitude column is not, we say not NA, that's Pandas for not missing, basically, or not an error in parsing. So all rows where the latitude's not missing, and all rows where the longitude's not missing. Those are the data we want to keep. Everything else we can get rid of. So we can't plot data that we don't know the location of. That's kind of impossible. So here we just get rid of those points. One other data massaging step we need here is we also have some where there is no current weather observation. And so we're saying anywhere where current weather is NA, where it is missing, we're going to set that to an empty string here. And so that's all of our initial data manipulation here. Okay, and that runs, goes through the parser. And so we can see what we have in surface data now. And so this is a pandas data frame if you've not seen one before. We have all the rows of different station, indexed by the station ID, columns with the station ID, the latitude, longitude, elevation, and a variety of other observed columns like air temperature, dew point temperature, and whatnot. So that's a pandas data frame right now. Now in MetPy, our calculations, we want unit information so that the calculations are all correct. It can work properly. So I'm going to delete this cell and go back to what we have in the notebook. So we have a helper function in MetPy that says pandas data frame to unit arrays. So we're going to take our data frame, SFC data, and here we also pass it the SFC units that we saved off earlier. And that allows us to convert from a data frame to a collection of individual arrays with unit information as appropriate. And so now if I look at SFC data, instead of that nice different columns, we have what Python is, it's a dictionary where you're mapping a string name, in this case, a column name, to an array of data. So we have the station ID array, and we have the latitude array, wind direction. This just makes it easier because then we can easily attach unit information. So for instance, our wind direction array here, excuse me, we can see has units of degrees, or wind speed has units of knots. We like doing this automated unit information because it makes it easier to work with data that come from a variety of sources. So you can better write scripts that interact with a variety of data, and you don't need to know, you can take the unit information from the data and not have to hard code them in your scripts and have your calculations come out wrong or your plots come out wrong by having incorrect unit information. So that's what we're trying to do. Okay, so we downloaded some data. We did some initial cleanup by removing missing points and places where the data weren't in a form we could work with it. So now the last step. So Metars. So here's an example of what some of a METAR observation looks like. You have the site ID, this time code, which is 02, the day of the month, 1613 time in Zulu or UTC. And then you have some text coded things like 1/2 SM, that's the visibility in statute miles. You have the current weather conditions. You have this text code, a variety of text codes that represents the current conditions. In this case, you have a report of SN, that means snow. And then you have maybe the sky cover. So in this case, that's overcast at, I believe that's 2,500 feet, but I'm not positive about that. It's been a while since I've done these by hand. What I want to focus here is this SN. We're trying to convert SN into a code we can use to make a plot. So as is in this diagram here, we take SN and we need to convert that to a standard numerical code defined by the World Meteorological Organization. So we want to take that, convert it to 73, that's the WMO code for snow. And then we want to convert that into a pictogram representation of that. In this case, the 3 stars that represent moderate snow. And so we can use this function wxcode to numeric, and that's a function in MetPy that takes these a list of these or array of these text codes like SN and converts them to the appropriate value of 73 or whatnot, depending on what the actual observation is. And we have the link here to the doc string for that. So as a quick activity, we want to create a new array here and store it under the key WX code in SFC data. And we want to convert the text weather observation to the WMO numeric code. And so what we're asking for you to do here in this activity is write the correct syntax using WX code to numeric with the right data using the current WX1 key to convert those two, or convert the one form, the text form, to the numeric form. We'll take just a few minutes to let you all try to do that, and then we'll go through it. Okay, I think it's probably a good time to start walking through this. So, if anyone else wants to put their solution in the chat, feel free to do so. But I did see at least one, saw this as common across some solutions. So yes, we do want to use WX code to numeric. I'll start with the first solution I saw, which said we're going to pass SFC data to it. So if we run that, okay, we got no error, so it must mean the code worked, right? Not so fast. Always double check that the computer's doing what you wanted it to do, not what you told it to do. So if we look at what happened when we ran it that way, we got an array of all zeros. Well, that's not really what we wanted. So let's look at what happened. What we did was we passed all of the entire dictionary of SFC data to WX code to numeric. And so that ran through each of the columns. So that when, as a way to kind of look at what it was doing, we can say list SFC data, and that'll convert it to a list. And what you see is we get individual column names. So what we wanted to do is we wanted to loop over all of the weather codes for each of the stations and convert it. Instead, what it did was it looked at each of the column names and tried to convert that to a numeric code. And since it doesn't have a numeric code that corresponds to station ID or latitude when it's expecting SN or RA for rain, it just gave back 0, which is basically, I have no idea what you're talking about. So passing just SFC data doesn't quite work right, but if we give it current WX1, one particular column of all the current weather observations. Now, if I look at what's in SFC data WX code, we do see some zeros there, but we see a whole bunch of things in the middle. See if I can get to print them all out. With NumPy, sometimes it's problematic, yeah. So usually if I want to validate that interesting things are happening, I'll say .max, and then I can see what the maximum value is. Okay, maximum value this time is 95. So it is doing more than just assigning zeros here. The other quick check I do was last time we got about 16 values or something. I can look at the length and see we got 8,600 values. So that gives me some more confidence that the code I'm writing here is working correctly. The other way we'll verify that it's working correctly is when we make the plots, we'll see the weather symbols as we expect, but we'll get there in a minute. It's a good call in the comments that you can do .toList to see all the elements. Yeah, that converts the array. I'm not sure if I want to actually see all 8,600. That's going to be really noisy in my notebook. So, all right, other activity here. We need to calculate, to make our plots, to make WinBarb plots, we need U and V wind components. So METAR reports don't contain the components of the wind. They contain a speed and direction. And so what I would like you to do is go look at the documentation for, I guess, where are we, to break time? Yeah, we are at break time. So before we go to this activity, let's go ahead and take a 15-minute break, and then we'll come back and we'll walk through this activity. But if you want to work ahead during the break, feel free to do so. Go to documentation and the code sample we linked here. But otherwise, we'll take a 15-minute break. I'll start the timer, and then feel free to ask any questions in the chat or in the Slido. And yeah, see you in 15. All right, well, we're back from break now. And yeah, let's get into our exercise real quick. So the activity is to calculate the U and V wind direction. And so we're trying to use the wind components function from MetPy to calculate wind components from the speed and direction values we have in the METAR reports. And so we've pointed you to the documentation for wind components. We've also pointed you to an example from MetPy's documentation that uses the wind components. And so the activity here is to write the U wind component to SFC underscore data square bracket U in quotes, and the V wind component to SFC data V. So if you haven't done that already, go ahead and work through that and put your hand up when you have done that, so we know where you all are and we can figure out when we should move on, since we're coming off a break here. Okay, so here's what we're looking for on this. If anyone wants to share their answers in the chat, now's a great time to do so. SFC data U and SFC data V equals mpcal dot wind components, wind underscore components. Tab completion is your friend. And then another part, companion to what Drew shared earlier with the question mark is if you have typed a function like this with the parentheses and you're sitting here wondering what to type next, you can't remember what the order of the arguments is. If you hit Shift and Tab, Jupyter will bring up the signature by default here. And we can see that the signature is speed and wind direction. So that would be SFC data wind underscore speed and SFC data wind direction. And see if I run that cell, it works. So this uses what is essentially the ability to return multiple objects out of a function in Python. And so we can take the multiple values that are returned or multiple arrays that are returned here and put each one of those into an entry in the SFC dictionary. There's nothing wrong if you did it, slightly differently, as long as you had to eventually get the two values into SFC data U and SFC data V. As been pointed out in the chat, already in the SFC data dictionary was eastward wind and northward wind, which eastward wind is exactly U and northward wind is exactly V. I'd like to say that was some kind of planned educational opportunity, but honestly, we've had so many community contributions to MetPy that I had missed that eastward wind and northward wind were already done for you. I would make you actually work through code that wasn't all that useful, but at the same time, I think it is good to expose you all to the multiple value unpacking and working through another example of practical use of MetPy's calculations. But now we all know that MetPy actually has that in there for you to help save you a bit of typing. Okay, so there's our U and V wind components. Now the last step is we want to make some pretty pictures. And so we've walked through all this data preparation. Now we want to make a station plot. And so the station plot's a frequent way that point data or observations are visualized, either for surface data or sometimes upper air soundings and things like that. And so what we're going to be looking at is we're going to be trying to plot the air temperature, the dew point temperature, cloud coverage, the current weather symbol, or the symbol representing the current weather, and then the wind speed and direction as a wind barb. And so here's a nice drawing of what we're trying to get to. And so what we're doing is we're plotting the cloud coverage here at the center. with the wind barb going into it. We're going to put the symbol representing the current weather here to the east of the center point. And then we're going to put the air temperature observation to the northwest of that center point, and then the dew point observation to the southwest of that. And so this station plot observation kind of breaks up, you have a center point that you're plotting at, and then it breaks up the area around it into various portions of a grid denoted as north, northeast, east, southeast, and so on. Often plots, the canonical way, if you're doing it in color and not black and white, is to maybe do dew point in green. But then for color deficient vision, it's better to use blue rather than green, just so you get the differentiation of the colors for those who might have trouble distinguishing between red and green. And then usually often you'll put the current weather here to the west, and then you'll have a bunch of other observations to the other side, and we're just trying to spread things out for this plot. But the nice part about MetPy station plot functionality is you have control over all of this. Whatever observation you want to put in whatever box up here, you have that freedom at your fingertips. Okay, so here's how we're going to make our plot. And so just like we did start before when we were plotting our contour plots, we're going to create an axis. And we're going to use the the projection that Rtma uses. So it's another reason why we pulled that out before, so we can reuse it in later plots. So projections Rtma CRS. Our first step here, and let me go ahead and wrap this line so I can see it, is we start by creating a station plot using the station plot class out of MP plots. When we create that, we tell it what axes we're going to draw on. We give it the longitude and latitude of all of our stations. And when we pass those in, we use this .m, which is short for dot magnitude, because for reasons, a lot of the plotting software doesn't like us giving it lats and unit arrays. So we use this to say, okay, we don't need the unit information here. So that's what the .m does, is get rid of the unit information. And then last, we pass in, just like when we use other plotting functions with Cartopy, we pass in the transform. Here we give it the CCRS plot Curie, which is how we denote that these are longitudes and latitudes. From here, we're going to populate the various portions of our station plot. So we called our station plot STN, and here we say STN plot parameter. We tell it what part of that grid we want it to be, so the northwest. We're going to give it our air temperature. We tell it the color should be red. Do the same thing here with dew point temperature, just plotting it to the southwest, and we also make it blue. And here we want to plot some symbols. So we can say STN plot symbol. And that's so we're trying to take these various values and we want them plotted as special symbols. So here at the center, we're going to be plotting our cloud coverage. We give it surface data cloud coverage, and then as the second argument, we need to tell it how we're mapping various values to symbols. And so I will pull up here our cloud coverage. You see we're getting values 0, 6, 2, 4. They just kind of represent portions of the sky that are covered. And you get those out of the METAR observations. This MP plot sky cover tells it how to convert those values from 0 to, I think, 8. I think maybe there's a special value of 10 in there. But this tells it how to convert that to a particular symbol. And so this is the converter that converts sky coverage symbols. We also have one here using plot symbol to the east. We'll do that with the WX code values we converted. And we tell it, use this MP plot's current weather converter to convert those codes to the exact symbols we want to plot. Then last of our observations, we're going to tell it to STN plot barb, so to plot a wind barb, and we give it our U and V wind components. And then just to finish off the plot, we tell it to plot coastlines, and we set the extent, the bounds of the map we want to plot. So we're going from -113 longitude to -70, and we're going from 25 to 45 degrees in latitude. And if we run that, It takes a little bit of time. And then we get a mess. So remember earlier when we looked at our data, we had 8,600 observations. That's a lot of observations to try and fit on a single map. It tried to do it for you. You got what amounts to a garbage plot. So we need to do something to try and reduce how many of these stations are being plotted at once. And so we have some functionality in MetPy to make that easier for you. And so we come down here. We have a few lines at the top to try and make this more legible. So here, and we had a question earlier about converting lats and lons. Here we're going to use our coordinate transform that represents the Lambert conformal projection that the RTMA was using. We call this transform points method. We pass it the source projection, in this case plot Curie, meaning we've got longitudes and latitudes. We give it the x coordinate, which is longitude, again using .m to remove the unit information. And we give it our y coordinate, which is latitude, again removing the units. So that gives us our locations now, transforming our longitude and latitudes of our station locations into the domain that we're plotting into. Then for MetPy Calc, we call this function reduce point density, and its mission in life is to serve this kind of use case where we want to reduce the density of points to a certain spacing between the stations, or minimum spacing between the stations. We get our locations, and this is saying we really only want the, after we transform, we only want the x and y locations. We don't care about it. It actually gives you a vertical coordinate, but we don't want that. So we're just going to say give it the x and y as the first two coordinates. I wanted to space them out every 175 kilometers or 175,000 meters. And what that returns is this mask. Basically, for every station, it gives you a true or false value. True if the station should be kept, or false if the station should be ignored. And we'll use that in a second to simplify our plot. The other thing we're going to do is we're going to create a figure manually and specify the figure size so that we can get a bigger figure on the screen, because that'll also help us have better ability to space out those stations. So in this case, this is 20 inches by 10 inches. Now we're at a pretty high DPI, so it should fit pretty well on the screen. Everything else, the axis creation, we in this case, we say fig.add subplot. So we have our figure created, we say fig add subplot to add the axes to it, still passing the same projection. And then let me wrap some of these here. Okay, so we create our station plot again, give it the axes, give it the longitude, but now when we pass in longitude, we first index it with plot mask. And so when you have a NumPy array, or I think it even works with X-array too, you can give it that mask of true false values and it'll select out only the points where this array has true. So you're giving it an array that has one value for every value that's in this array, but you're only going to select out the ones where this is true. And so that's an easy way to try and reduce our points. So surface data, give it the plot mask, do the same thing for latitude, give it the transform. We also pass here clip on equals true. That tells it that we want it to not draw the stations outside our plot. Here we call plot parameter again. We give it our surface data, our air temperature, and then we also here say square bracket plot mask. We'll stop with that for now. We'll just run this and see what happens. Same finishing touches as before, but now we see we get a bigger plot and we also get much more spread out stations with just the air temperature value. So the activity here, it'll take, I think about 10 minutes, is to, using plot mask, duplicate what we did above here with the other plot parameter calls and the other plot symbol calls and plot barb. Maybe we'll call those, and your goal is to try and make those work with the plot mask so that we can have a full station model plot here with that. And maybe we'll take, maybe given our time, take about 5 minutes here, and then we can walk through the solution.
And of course, don't hesitate to let us know if you have any questions or issues. And be sure to raise your hand if you get these completed station plots visualized. Brian, we have a question in the chat about specifying the mask. Do you want to really quick point that out and show that one more time?
So the mask here is we're calculating that using this reduced point density function. And essentially what that's doing is that's looking at all the locations we gave it and trying to pick out one and eliminate all of the other points that are too close to it. And it keeps doing that for all the points that you gave it. So here we've given it all the locations of all of our stations. It's essentially selecting one point within a circle of 175 kilometers. That's what it's doing. For our purposes, in terms of using it, what we need to know is this is giving us back an array of true and false. So if we look at plot mask, we see this is just an array with true, true, and there's a bunch of stuff in the middle, false, false, false. So that's giving us back whether for each station that we have, whether or not it should be plotted, or whether or not, you know, whether we want to keep it or not when we use this mask. And so then when we pass that into, so here I will create a simple example to show you how this works. So I'll make an array. I think I'm gonna need this. Okay, so we have an array of data, 0, 1, 2, 3, 4. And so I can go R, true, false, false, true, false. So I'm keeping 0, getting rid of 1 and 2, keeping 3, getting rid of 4. So that's what this mask does. It say which, run through each of the values and what ones do we keep, or what ones do you keep, and false for ones we want to get rid of. And so that kept 0 and 3. We're just calculating what that mask should be here and then passing it in when we do all of our operations for plotting here. We're only handing it the longitudes for stations we want to keep. We're only handing it the air temperature values for data we want to keep. Same kind of thing as what we're asking you to do here with plot parameter for the dew point, and then to do the same thing with plot symbol for cloud coverage and WX code, and as well for the wind barb. It's good to clarify this because this is a really cool tool to have at your disposal for when you want to work with various data, because you can think you don't just have to do this for manually creating true false or doing plot mask, but you could use this to select data greater than a certain threshold, select data less than a threshold, things like that. Okay, so I think we'll just go ahead and start working through the solution, and I'll go ahead and type this out so you can see me do it and fumble around. So we're going to plot to the southwest. We want the dew point temperature, and we want to give it the mask so that we only get the dew points for the points we're keeping. We're going to make that blue. And we want to plot symbols. We want that, the first one, the sky coverage in the center. And use the fact that we can tab complete dictionaries in the notebook. So I don't have to remember what that was called. And we need to give that the converter for the symbols. So it'll be plots dot sky cover, station plot symbol. And then we said to the east, we want the sky or the current weather. So surface data weather code, plot mask, MP plots, current weather, color equals, I think we made that blue too. And then station plot barb, surface data U, plot mask, surface data the plot mask. All right, let's see what happens. Ha. All right, so there's our completed station plot. So with that, I'll turn it over to the poll here.
All right, I'm seeing the responses slow down here, so let me reveal our correct answers and then we can talk about it.
All right. So select all the following that are required for creating a map of surface station plots using MetPy. So yes, we do need surface observations. Do we need IMShow? No, we don't use IMShow for surface station plots. We use print? Not really. We did use a station plot class. And then the last one, Metar class. Well, there was no Metar class we used. We did use some Metar data, and we did definitely use the parse Metar file function, but there was no Metar class. So Nicole got you with that one. All right, and with that, I will turn it over to Drew to close out our session today.
Okay. So we're going to spend the remainder of the time putting together that plot we previewed at the start. It's literally one cell of code. It's a lot of code, but I'm going to chew through it and explain everything, or at least point out what is happening. I would suggest anyone following along in the notebook, go ahead and run the cell. Depending on your computer, this cell could actually take on the order of a minute or two or a few minutes to fully execute, because we are going to regrid our satellite data, and that can be, because of how Cartipy does this, that can take a few minutes, depending again on your computer hardware. We're going to have some time at the end for space for people to play around with it, sort of make this plot their own. But I definitely encourage that as we walk through this, because this is what we'll be spending the rest of the time on, to ask any questions you have, or let us know of any issues you're running into trying to run this. So I'm going to skip back up to the top actually to show what it is that we're trying to accomplish. So we're trying to create this single image that combines all of the things we've explored individually today. So on this visualization, I have satellite data in the background. I have my contours of Rtma output in blue, and I have some station plots of surface observations. We also have some other features on here we'll add and play around with, but this is what we're going to make. So let's get started. Let me go back to the bottom. I'm going to follow my own advice that I gave you, and I'm going to go ahead and run this cell, because even on my computer, this could take a few minutes. But while that's running, let's walk through start to finish what we're doing here. So we had a question early on about Matplotlib Figures, because we're trying to sort of make our final product, or like production quality plot. Here we are going to specify the creation of a figure so that we can customize it. In this case, the only thing we're customizing is its shape. So we want it to be 20 by 10. on our screen, there are different ways you can specify the shape of your figure, but this can control its aspect ratio and sort of the DPI or resolution of it when you go to save it or print it, etc. Now, we've made a figure. We're going to use the ability of Matplotlib to explicitly create an axes object on that figure using fig.addSubplot. These ones here are just indicating where we are putting our axes object. Since we're only making one, don't worry about it. As before, we need to specify the Cartopy projection that our actual map will be in. And as before, we've decided we want all of our information. So we want our satellite, we want our RTMA, and we want our surface obs to be projected onto a map in the same projection as the RTMA output. And that was a Lambert conformal projection. But we still have that saved from earlier as RTMA CRS. So we're going to specify that in this projection equals. So now we've got a figure that we can control. We've got our axes object plastered into the middle of it. Now we're going to go through and we're going to revisit the steps that we followed to get here to basically go through and add each of these products to our map one by one. Now, the first one is where your computer might struggle a little bit, because when we take our original satellite data and we want to change it from its given projection, its geostationary, I think, projection, into our Lambert conformal projection, to preserve that information as best as possible in displaying an image, Cartopy needs to basically know how high resolution we want to make that transform, because that can be kind of expensive for your computer. It can take some time if you want it to be a very high resolution image to go from one projection to another. So what we're doing is we are specifying the extent of our image using the original CMI, the original satellite data arrays X. So remember, if we use metpy.x, this is a shortcut, regardless of if it says lat, if it says lon, it says x1, x2, whatever. This will find our X dimension. So we're picking the 0th element, or the very first X value in that dimension. That is our first point in our extent. Then we are picking the last, so -1 value in that same X dimension. That is our second point of our extent. Then similarly, we are picking the first and last Y value to sort of draw the boundaries of the satellite image we want to display on this map. Then we need to still show our image as we did before with mshow of CMI. We need to give it this extent so it knows where the boundaries of this image are in space, like in our new projection. You can specify where the origin of this image is. If you have maybe a satellite image that is for some reason mirrored, or there are a few reasons you may need to specify this. But if we've drawn our box, we may need to specify if that's starting in the lower left or in the upper left. Here, as we explored before, we're going to specify our color map to be this reversed gray color map. And then the one that might slow your computer down, I'll bump this up later, but this regrid shape is basically telling Cartopy, hey, I need you to adjust the resolution of my image when you transform it so that my computer doesn't take actual minutes to get this done. We picked a relatively low number here for your context. I'll be bumping this up to like maybe 6,000. In fact, I'll go ahead and do this now and then rerun this plot. If I go ahead and show you for comparison, we have a kind of pixely plot right now. I'm going to rerun this. Maybe save this yourselves if you plan on doing this, because you might, especially if you're on a laptop, you might be dealing with jet engine fans and a few minutes of Python running, heating things up. So maybe another time. But we need to tell it how sharp we want this projection to be. And then, as usual, specify the projection that our data is originally in. So we never did this earlier, but similar to our RTMA X-array data set, we are having MetPy pull out with .metpy.cartopy.crs the exact projection information, embedded in our CMI data set, so it knows what projection to go from to. So this will be its geostationary projection, I think it is, with all the necessary information. Again, I don't suggest bumping up this number right now. So I would show these one step at a time, but because this could take a little while and because we've already done it, I'll just have you trust that this is what is putting the grayscale satellite imagery onto our plot. So then let's move on to the next lines of code. Next, we want to add our contoured values of theta E from our RTMA data set on top of our satellite imagery. So just like we did before, we're going to call Matplotlib's contour function with ax.contour. We're going to specify the x and y of our theta E the exact same way we did before. Then we're going to specify the values themselves of theta E. Here for contour, we're going to explicitly tell it the levels we want contoured. So what we're saying here is I want you to plot the levels from 240, so values of 240, to values of 400. Remember, these are Kelvin, theta E in Kelvin. And I want you to give me 8 of these. So space out 240 to 400 by 8. We're going to make the color blue. And then again, we are going to specify the original projection that this data, so this is theta E .metpy.cartopy.crs, the original projection of the RTMA data. In this case, it doesn't need to change anything like it does for the satellite data, but we need to give it that information so it knows what coordinates we're working with. So now, if I were to stop here and make a plot, I'd have a plot with the satellite imagery and blue contours of theta E. So let's continue to add our station plots from the previous exercise. We're adding a few extra tidbits here. We suggest that if you want to explore this further, there's a lot more information in, say, the Matplotlib documentation, etc. Like if you really get to where you're wanting to make this your own, there's some room for exploration here. But we've added in a few extra things that I'll explain when I get to them to make things a bit more readable, especially on the gray background of our satellite imagery. So as before, the first thing we have to do is we need to make a station plot class on top of our axes we've created before we can add anything to those station plots. So we're going to create station plots on our AX axes that we created up here at the top. We're going to, just like in the previous example, specify the longitudes of each point masked. We're just going to use the same mask we created before. And we need, just for the locations here, we need to use .m to specify the magnitude of those unit arrays because it doesn't like unit information here. We'll specify their latitudes, so their longitude, their latitude. Because these are lat-lon, we're giving it information in lat-lon. We'll specify its transform as the Cartopy-CRS Plat Paris. We're going to specify that for each of our station plots, sorry, ignore the train, the font size will be 11 points. Here, the symbols are themselves fonts, so this is sort of scaling the symbols and the text fonts that we're putting here. I've actually forgotten what Z order specifies. So we can come back to check that. We'll call that a learning opportunity. And clip on equals true is something we need to specify that will allow Cartopy to prevent us from drawing station plots outside of our extent, outside of our image extent. So this sort of draws a hard boundary at the image, extent of our image. So once we have these station plots in place, we can, just as before, add parameters, symbols, and barbs to each of the station plots. So we'll go through in order as we've done before. To the northwest of each station plot, we're going to add air temperature. We've masked it so that we don't have that giant illegible mess. And here we have manually specified RGB values for color. It's still red, but we've sort of changed the red and the blue here to be more legible on a gray background. This is something that came from trial and error, and we just manually specified. So this is something you might find yourself doing as you make these plots. But these are just RGB values for our colors. Now we've added something from Matplotlib here. We imported at the very top. We've added a stroke or with stroke path effect. Don't worry about the naming here, but basically what this means is we've drawn text borders around, or we've drawn borders around our text font. So this again allows us to make our red and blue values for air temperature and dew point temperature a little more legible on a dark background. Now, similarly, we will plot our symbols. In the center, we'll put our cloud coverage. We've masked it down. We need to tell it what symbols we're actually plotting and how those correspond to our values. And this time, because we're on a generally gray background, we're going to pick a bright white for our symbols. You would have seen that in the preview image. Excuse me. Similarly, we will be plotting our current weather, which someone has pointed out there isn't actually any showing on our map right now. This is working, but there's just not very many current weather reports from this Metar, and we filtered all or most of them out, actually. So to the east, we'll be adding our weather symbols, if they were there. These are masked, just as with our parameters. We've specified our color blue here to be a bit more legible on this map, and we've added a border around it to make it, again, a little more readable. And then finally, we're going to plot our barbs, our wind barbs from the UNV we calculated, definitely calculated earlier, and again, specify those to be bright white. A couple extra things we're doing differently for this plot, just for your own knowledge, is that instead of just typing .coastlines, if we want to add a feature and have more control over how it looks, we can use Cartopy's add feature, and you can go look, their documentation for features can guide you through what options you have here. We, at the top, imported Cartopy's library of features that you might add to a map. And so we're in this first line, adding the feature of Cartopy's features borders. So this is the border of the US, or in this case, we have international borders. And we specified that we want this to be yellow, again, to stand out against our dark satellite imagery. Similarly, we are specifying the Cartopy feature coastlines, and we're specifying that we want it to be yellow. And then finally, we've drawn a box around the whole thing, sort of zooming in our extent in longitude and latitude that we actually want our plot. And then we decided to just go ahead and throw a title on there. We've done some fancy Python string formatting here to basically pull out the time that we got at the very beginning from our satellite observation and read it in and put it in the title of our plot for us. Niftily, you might see that we've also included a sort of math text theta E here in our plot title. If you specify the string type R here at the start before you start typing your string, you can have this sort of capability. And then finally, shameless plug, we have a built-in MetPy plots, add MetPy logo, so you can let people know the wonderful tools you've used to get to your neat plots. And like I said, I started this a minute or two ago after bumping up the resolution because even on my computer it would take a little while. But we got there, and it's a lot less blocky, and it looks pretty good if I say so myself. So we're near the end of the hour, but we've left some room in here for suggestions for ways to modify this and make it your own. And of course, we will be available to further explain any of this and sort of decisions we made now, and to answer any questions, offer any feedback, and any guidance in playing around with it. So yeah, that is the end of our notebook.